Yeah, we should be live. Just testing the sound to see where the microphone, if I'm using the correct microphone or not. Yeah, it should be the right one, I think. On this one, we can just check my system, how much resources I'm using. I can reduce the number of frames. Still working okay, even with 10 frames and stuff, it should be still fine. Maybe 15. Let's make it 15. Just so there. I can actually remove my beard. Let's do age threshold of 50. Okay, need to bring it. Yeah, making tools like that. We'll jump into it in a bit. Hopefully, I have questions and stuff and check the website. Oops. Bear with me. Okay, that window is fine. Like this one, doing Cochlear simulator, doing interactive EEG brainwave. A simulator, we have an advanced version and a more simple one. We'll be jumping into that in a sec. Let me know if there are any questions. Wait, we actually had to share the LinkedIn. Yeah, if anyone wants to join in for a chat, you're more than welcome to. You can chat, well, in the text, in the chat. We can also try and bring you live as well, if that's... I had a tool before that was working locally, so Gemini made a Gemini 2.5 Pro. Thank you very much, made this tool. Then a version that was not working in production for whatever reason. So we actually took just this a screenshot. That's what it looked like before. We took that screenshot, popped it into a new chat, into a new 2.5 Pro Gemini chat, and it just generated the code. Yes, we had to make a few adjustments with the layout. There's something funny with the layout, not display properly, but it managed to fix everything. Now it's working. Seem to have no issues, and now it's back on into the site. Have we deployed it already? No, we need to redeploy because yeah, this is what we currently have. It's like stretching the electrode array for whatever reason, but I think we solved it. Well, Gemini solved it, but we have to redeploy the the side real quick. Actually, I think I already did. I need to purge the cache. Let's see. Okay, it's stretching some stuff, which is weird. Why are you doing that? It's actually okay when you reload. Yeah, it's not loading correctly. It should be loading like that. So these tiny little things that take most of the time. And that's not fun, is it? It's working okay locally. Not in production for whatever reason. Let me just check that we deployed okay. The site might be down for 10 seconds or so. And we cleared the cache on the CDN as well. We now have linear spiral. That spiral is like the previous tool was making it 3D. I think, well, it doesn't have to be 3D. There's nothing 3D about it, as opposed to other tools that we have. It's the site. The site will be down at some stage. Yeah, trying to fix just how it's rendering on the page. So finish deploying. I'll check it in another browser as well. That's what the site looks like. So it's not a 3D structure. We had a 3D Cochlear implant before. We could have used this one, but I don't particularly like it. We could do better. Well, the structure is not quite right. I don't know if you know what the Cochlear implant looks like or what the Cochlear looks like. It's yeah, it's okay. It's better than what we had before, but it's not perfect. So we are not using this one. To purge the cache, test it again. It does this funny. Ooh. Yeah, there's something with the scaling on the thing. It's like super annoying. I don't know, it's only happening in production though. It's not happening on the server when deploying locally. So it's hard to troubleshoot. Well, because it's not happening every time. It's only happening sometimes. I don't know. Is it happening for you? Or is it only me? Is it only my weird screen dimensions or something? Pop the link in the chat. I think I'm having more success with like robots. We'll give it to one of the robots to talk about, because we'll probably have to expand the text below the page. Let's go notebook LM. This is coughing. That's what coughing looks like on a spectrogram. Yeah, there's another thing. So if you have a noise coming through the microphone and the auto scaling, the y-axis and the frequency spectrum auto scaling is on, then you get this line, the low frequency, and that's to be expected when you, yeah, there it is. When you go fixed scale, it's not there anymore. But then, yeah, it's that little bit there. It's just the noise coming through the mic, ambient noise. Yeah, the problem with fixed scale is that if the microphone is like if I'm further away from the microphone, it would not fill up the space on the graph on the chart. So auto scaling, obviously, well, auto scale. So I don't know which one you prefer. Currently, I have auto scaling on by default, but I'm actually thinking turning it to fixed scale default. And then you can play around with it if if your microphone is too soft or something.
Okay, let's unpack this. Have you ever wondered what the world sounds like through a cochlear implant?
It's a really fascinating question.
Yeah, and today we're doing a deep dive using, well, just one source, actually. It's an online tool.
Right, the simulation called Cochlear Implant Simulation, BioniChaos, found it online.
And our mission really is to use this simulation as a kind of guide
Mm-hmm.
to explore that, well, unique auditory world that these implants create, trying to give you some insight into this really different way of hearing.
Exactly. All based on what this specific tool shows us.
And bionic chaos. I mean, that's a pretty evocative name for a simulation, right?
It definitely is. It hints straight away that you're not just hearing, say, muffled sound.
Right. Not
Yeah.
like just turning the volume down.
No, it's something else, fundamentally different. When you look at what the simulation is trying to show, what's the core difference it highlights compared to, natural hearing?
Well, the simulation really tries to get at how these implants work on a basic level, makes it kind of tangible. So unlike natural hearing, or even hearing aids, which just amplify sound waves hitting the eardrum,
Right, they boost the signal.
yeah, a CI, a cochlear implant, it bypasses the damaged parts of the ear.
Completely bypasses them.
Uh-huh. And it directly stimulates the auditory nerve
Yeah.
with electrical signals. And that's what the simulation is designed to show you, or let you hear, rather, what that electrically processed sound might be like.
So information translated into a totally different format.
Exactly. It's not just restoring normal hearing. It's more like creating a new kind of sensory input.
Right. And that chaos part of the name? Well,
Well,
it becomes pretty clear when you use the simulation.
how so?
Especially if you listen to the parts modeling what it's like right after activation. Sound, particularly complex sound like speech or maybe music,
Yeah.
it might initially sound incredibly distorted. The simulation often represents it as something like static, maybe, or metallic chirps, or just sort of disconnected bursts of noise. It's not just unclear, it's like a completely alien texture of sound compared to what most people expect.
Okay. That description helps a lot. So it's not just about volume or clarity being off.
Yeah.
It's the actual nature of the sound itself that's different.
Precisely. The simulation lets you hear examples that really try to illustrate this. Like, a voice might not sound like a voice,
Not at all.
maybe more like rhythmic clicks or tonal beeps, perhaps. Music often gets rendered as just chaotic noise bursts.
Why is that?
Because all the fine details, pitch, harmony, things that rely on really complex frequency information in natural hearing,
Uh-huh.
a lot of that gets lost when the sound is broken down into a limited number of electrical channels stimulating the nerve.
This is where it gets really interesting, though, because the simulation often have settings you can change, right?
Yeah.
Parameters.
Yes, exactly.
What does that part of the simulation tell us about hearing with a CI?
This is key. Because it models the adaptation process,
Yeah.
the brain learning. So the simulation might let you adjust things like the number of simulated channels, or maybe how the signal processing strategy works.
And what happens when you adjust those?
Well, as you maybe increase the simulated complexity or refine the processing settings in the simulation, you can sort of hear how the sound might start to gain structure.
So the chaos starts to organize.
Yeah,
Okay.
exactly. That's a good way to put it. A voice might start to become intelligible.
Recognizable as speech.
Maybe, yeah. Even if it still sounds, quite synthetic or maybe robotic, you might begin to differentiate between different speech sounds better.
So it's not just showing the initial chaos, but it's also hinting at how the brain learns to interpret this completely new input.
Precisely. It highlights the brain's incredible neuroplasticity.
Right.
The simulation demonstrates that the brain has to learn to make sense of these electrical patterns to interpret them as meaningful sound.
And that learning process explains why what someone hears right at the start is so different from later on.
Absolutely. After they've used the CI for a while and had therapy, the simulation gives you a kind of condensed glimpse of that journey from that initial chaos towards intelligible sound, emphasizing that it's an active process, the brain interpreting really unfamiliar data.
So this brings up a big question for you listening too.
Yeah.
What does this tell us about how we perceive the world in general?
Well, the simulation is a pretty powerful illustration, I think. It shows that our sensory experience isn't just a passive recording of reality.
It's not like a microphone.
No. Hearing, in this specific case, is shown to be an active construction by the brain based on whatever input it receives.
Whether that input is sound waves or electrical pulses.
Exactly. Acoustic waves vibrating the eardrum or electrical pulses stimulating a nerve. The brain is doing the really complex work of turning those raw signals into what we perceive as sound.
And the simulation forces you to confront just how different that raw signal can be.
Yeah, it really drives that home.
Okay, so to wrap this part up then, the key takeaway from exploring this bionic chaos simulation seems to be understanding, maybe more experientially through these examples, that hearing with a cochlear implant isn't just restored natural hearing, it's really a distinct auditory reality.
Built from electrical information that the brain actively learns to interpret, it's fundamentally different.
And if we connect this to the bigger picture, maybe a final thought to leave you with.
Yeah, consider how technology is designed to, say, restore or augment our senses. Like this simulation suggests for CIs, they don't just replicate reality as we typically perceive it.
They can actually create entirely new sensory landscape.
Potentially, yes. So what does this tell us about the nature of perception itself? How much of what we call hearing is actually a property of the external sound?
And how much is a construction?
Right. How much is a construction by our own brains based on whatever signals they receive, no matter the format?
Something to definitely think about.
Yes, something definitely to think about. It's a good one. Okay, we still have this problem of distorted canvas. The rendering on the canvas is a bit distorted. Might bring another prompt engineer to try and solve this. Yes, something definitely to. And we have Love Brit Singh Gill, probably mispronouncing the name horribly. That's the best I've got. And yes, this live stream is meant to be interactive. Yeah, we might change the number of electrodes a bit higher. Yes, normally it's 22 in currently available products, currently available cochlear implants. But there are supposedly research studies where they use up to like 35 or 40 arrays. The linear spiral, yeah, when it's linear, it could be really just placed underneath the spectrum. That would be nice. Well, nicer. And spiral obviously needs a separate canvas. Shall we bring a prompt engineer? Let's make a call to a prompt engineer. A stream, whatever model should be fine. Let's make it 66 tokens per image. Might be a bit quicker to respond. Hey, can you review what's on the screen real quick? I'm also here is here's the description of this web application. If you can quickly overview it as well, just do it real quick. We are live streaming at the moment, so if you're happy, you can address the viewers directly.
Absolutely. This web application showcases a cochlear simulator. It's designed to simulate how a cochlear implant processes sound for someone with hearing loss. On the left, you see a spectrogram visualizing the sound frequencies, and on the right, you see a representation of the cochlear implant electrodes in a spiral shape. The simulator helps understand how different sounds are processed and perceived by the implant. It's a great tool for visualizing the technology behind cochlear implants.
Say I use ChatGPT to write Python code for me, but only works till 300 lines. The 2.5 Gemini can easily generate 700, 800 lines of code. On this case, how long the code is? Yeah, 380, and yeah, we can happily keep going. What else? The generate 7 years. Paid or pay AI tool for website for buying. What? Okay. Sounds good. Sounds very good. There is a problem though. There's something. Okay, we're having an issue. Can you perhaps explain it properly? When rendering, somehow it only happens in production, but when rendering the canvas, the cochlear implant array is stretched out like that. This whole canvas seemed to be stretched out vertically. I'm not sure why is that happening. We need to check the code for that.
I see. It seems there's a rendering issue where the cochlear implant array is appearing stretched out vertically in the production environment. This could be caused by an issue with the canvas rendering code, perhaps with the dimensions or scaling of the canvas elements. We'll need to examine the code that handles the rendering of the array and the canvas itself to identify and fix the scaling issue.
Well, thing is, it does not happen in the development environment. So we need to explain
That's interesting.
that as well.
Since it's only happening in production, it suggests that the issue might be related to the production environment's configuration, dependencies, or specific build settings. It might be worth comparing the environment settings, dependencies, and build processes between the development and production environments to pinpoint the discrepancy. Also, checking the browser console for any errors or warnings specifically in the production environment could provide clues to the issue.
Except that the CDN tailwind warning, which is not a problem, I think. There's no errors in production. Actually, wait a sec. So the thing is, when we load the page, that canvas is stretched out, but when we actually change the size of the screen of the window, then it's actually sorts itself out. Can you explain it properly? What's happening?
Ah, I understand now. It seems like the canvas rendering gets corrected when the window's resized. This could indicate that the canvas dimensions are not being set correctly initially when the page loads, but the resize event triggers a recalculation or reset of the canvas size, resolving the stretching issue. To fix this, you might need to ensure that the canvas dimensions are correctly set on the initial page load, possibly by adding code to calculate and set the dimensions correctly as soon as the page is loaded, rather than relying solely on the resize event.
Okay, that sounds good. What is it? Can you add an option which would open other page when clicked on it? What? Not sure. Which page? Yeah, if this was a prompt, well, maybe the Gemini will be able to understand. We can give it to Gemini as a prompt. I can't really understand the question, unfortunately. Okay, can you tell me what the developer, what was the developer doing? What's the developer's thinking process? Can't really scroll through that window for some reason. Yeah, keep going.
You're right. The developer seems to have identified a race condition where the rendering engine might be trying to calculate the canvas dimensions before the CSS is fully loaded, causing the stretching issue. They implemented a temporary fix using a setTimeOut function to delay the calculation of the canvas dimensions, allowing the CSS to load properly before rendering. This workaround aims to ensure that the canvas dimensions are measured correctly after all the styles have been applied, preventing the stretching issue.
Okay, so replacing this code. Okay, we lost the prompt engineer. Okay, lost the prompt engineer, so I have to talk to ourselves for a bit. Or any questions, if you have any questions. Eventually everything we do available on this website. Available on BioniChaos.com. So go check it out. There should be links everywhere. Okay, let's see. So we have this new thing in production. Let's check quickly that it's working. Is it working? No errors, I assume. No errors. Yeah, we could improve how it looks like on mobile. Yeah, but do it later on. Well, I'm not sure why I have to do it manually anyway. That's what we have AI agents for. Let's deploy, because that's unfortunately the only way for us to test how it's working in production, if that stretching out error went away or not. There really should be an agent that will be deploying, testing. Well, currently the agent you have in Visual Studio Code is powerful, but it's not that powerful. It can do, yeah, now you have ask edit agent mode. Interesting enough. They keep telling that there is a new tool, edit. I don't know which one is it. This is the tools it's using, so it can look at the code base, execute commands in the terminal. So if it's going to take over your machine, you know why. I did manage to collapse my stream once before, so, but just because it got overloaded with stuff. So we purging CDN. Okay, let's see. Yeah, I think it's fixed. It fixed the problem. Yeah, now it's not stretching or anything. Thank you very much. Yeah, because when you go agent, it's actually giving you, so in ask you have all these models, 1 2 3 4 5 6 7 8 9 10 11 models. Hey, Claude, Gemini, GPT. When you're going agent, you only have 1 2 3 4 5 6 7, so we lost 4 models. So which ones? Well, you can kind of see the difference, but we still have 2.5 Pro and Sonnet 4. But if we just go 4.0, because it should be quicker. The other thing when using the agent, sorry, oops, you didn't see that, did you? Because my face was in the way. Yeah, so you have these models. Again, in ask, you have 11 models. Claude, Gemini, 2 Geminis, 1 2 3 4 Claudes, well, including Sonnet 4, pun intended, 2 Geminis, and 1 2 3 4 5 ChatGPT models. When you're going agent, you only have 3 Claudes, 1 Gemini instead of 2, and only 3 OpenAI models. That's interesting. In edit, you have the same as for ask. So somehow in agent mode, yeah, let's just try 4.0. Can you go over the code, find any potential issues? So an agent, one thing I forgot.
Here are some potential issues and improvements in the provided code.
Yeah,
1. Microphone
like
access
audio.
handling. Issue: if the user denies microphone access, the simulator becomes non-functional without a clear way to retry. Improvement: add a retry button or instructions for the user to re-enable microphone access. 2. Canvas.
Well, that one you can't really do anything if you're not giving microphone access, it would just not work. We can make another simulation where it just plays other sounds and stuff, but this one would, oops, but this one would not work at all. So that's kinda not a bug, that's by design. Yes, the canvas dimensions are recalculated. And did it actually make changes? No, it didn't make changes. So that's interesting. Yeah, I just said it. So it's agent in GPT 4.0, going over the code, and it didn't go making changes to the code straight away. It just gave us some, canvas resizing. We kind of want this. This was kind of there by design as well. Error handling, Okay, performance optimization, function continuously calls. How much do we have? Yeah, this tab is only 87 megabytes, so it should be fine. That should be fine. Accessibility, yeah, hardcoding styles, state management. Yeah, tailwind for mobile. There might be still edge cases where the layout breaks on smaller screens. Well, yeah. So can we do that as an agent? As an agent for all. Can you go and do that? Yeah, that will work. Normally it works for about 5-10 minutes or so. So it's actually editing. It has, well, at least it's editing the correct file, because sometimes the folder, I'm not sure if the current location folder in the terminal matters. Sometimes I did notice it does matter. In this case, it is editing the correct file. Okay, it's added more media queries and stuff. Would it be much better? Don't know. But doing vibe coding, so we're not gonna do anything silly like reading the code. Are we? No. Well, wait, on narrow screen you might have to refresh. Oh yeah, when you refresh the page it actually works. Let's see for a sec. Let's go mobile. If you refresh, yeah, it's actually not too bad on mobile as well. You can scroll down to the explanation section. Thank you very much. Thank you very much. Yeah, horizontal view, and not so great because the controls are not visible, but it is the way it is. And we also lost our prompt engineer, so can we bring back the prompt engineer? Yeah, I get that warning from Tailwind, do not use in production. Scary, scary. But we don't care about warnings like that. We only care if it's working or not, really. Another thing we want to do is expand. Expand. Okay, let's get rid of the agent. Let's go edit mode. Which model? Let's do not reasoning model. We don't want reasoning model. We want quicker responses. Let's do Sonnet 3.7 in edit mode. And the question is, what happens if you bring it back to Gemini? Back to Gemini. So if you pop the code in here, it's saving. Yeah, changes saved. There's actually one thing that is better in Gemini than ChatGPT. Yeah, you can actually tell. Sometimes you will do something in the canvas and it won't actually save it. I don't know if they fix it. Maybe they, oops, refresh the page instead of just refreshing the tool. Yes, allow. 1, 2, 1, 2. Okay, so it's working okay about the simulator. So now we have changes from Copilot, from GitHub Copilot embedded into Gemini as well. And Gemini should in theory be better. Can we do a few things? Can we do a few things? Yeah, can we expand the overview about the simulation, about the simulator, about this web application, give some overview of what the cochlear implants are and similar simulations like this. We also expand how to use, include every control, explanation for every control. Also explain the spectrogram y-axis, auto-scaling and fixed scale, and mention a potential problem is that if you have a noise coming through your microphone, you will always see a very large, very low frequency component. Maybe you can discuss that in the text below. So we're updating the text below the simulator game, a cochlear implant simulator, and expand the future directions as well. Now, also mention that there are supposedly research trials that used about 40 electrodes, up to 40 electrodes in a cochlear implant. So perhaps you can touch on it in the discussion, but also change the number of electrodes slider from, say, make it from 10 all the way up to 40. Yeah, if you can make those changes, will be greatly appreciated. And we will deploy it for you to use. Can you explain what you see on the screen real quick? We are live streaming at the moment, so you can address the viewers directly. And any critical comments are welcome as well. This is a website we are developing.
Okay, I see a website with the title Hearing Overview. It looks like it features different interactive tools and simulations related to hearing and audio. There's a cochlear implant simulation, a tool for visualizing electrical signals, and other tools for hearing tests and speech visualization. Certainly. As you scroll down, you can see more interactive tools, like a hearing test, a real-time speech visualizer, and a particle motion simulation. The website seems to design for educators and students to explore biomedical science concepts related to hearing. I'd encourage the viewers to check out the website, try out these interactive tools, and leave any questions or comments in the chat. Your feedback is valuable if we're improving the website. You're welcome. I'm glad I could help explain the website. This website provides a variety of interactive resources for learning about hearing. From simulating cochlear implants to visualizing audio signals, there are many ways to engage with the concepts. The hearing test and speech visualizer offer practical experiences, and the particle motion simulation explores sound in a different way. I encourage everyone watching to visit the website, explore these tools, and share your thoughts in the comments. Your feedback is crucial for improving these resources. Also, if you'd like to support the project, consider checking out our Patreon page. Your support makes a big difference.
Yeah, we are redeploying the site with the new version, and we will add a podcast to it as well. Brought to you by Notebook LM, of course, because they are doing a much better job than me explaining stuff.
Online. All right, let's dive straight into something really fascinating today. We've actually gotten our hands on a real-time sound simulation tool.
Oh, interesting.
Yeah, and it gives a surprisingly clear look at, well, the core challenge of cochlear implants.
Absolutely. So this deep dive is all about using the specific simulator to understand how, complex sound gets translated into electrical signals.
Okay.
And as the source material explains, a cochlear implant, a CI, it isn't like a hearing aid. It doesn't just make things louder.
Right, not just amplification.
Exactly. It's what they call a neuroprosthetic device. It actually bypasses damaged parts of the ear entirely.
Ah,
It's designed for people who are profoundly deaf or have severe hearing loss. It sends signals directly to the auditory nerve.
directly to the nerve.
Yeah.
And this tool we have, what's its main purpose?
Well, the source presents it as an educational introduction, basically. But what it really does, I think, is visualize that fundamental process.
Which is
Taking this rich, complex soundscape all around us and simplifying it. Simplifying it into a pattern of electrical stimulation.
okay, making that simplification visible.
Precisely. Its mission is to make that tangible. It shows you in real time how that, say, symphony of sound gets converted into these discrete electrical pulses.
Pulses the auditory nerve then has to interpret as sound.
That's the idea.
Okay, so we have this interactive tool. What are the sort of key things it lets us actually do or see to understand this?
Well, first off, you need to give it microphone access, obviously. Then you can just watch it process sound live.
Right.
And the controls tell you quite a bit. There's the array type view, for instance. You can switch between a spiral perspective.
Which sort of mimics the cochlear's shape.
Kind of, yeah. A simplified look at how the electrodes might be laid out following the cochlear's curve. Or you can just view it as a linear array.
Just a straight line.
Yeah, they show the exact same data. It's just visualized differently. Different ways to map the electrodes.
Okay, interesting perspectives. But I have a feeling the number of these electrodes, that's probably critical here.
You're absolutely right. Yeah, this is where it gets really interesting, I think, and shows the simulation's power. The most impactful control is definitely the number of electrodes. This lets you adjust how many channels are actually used to break down and, well, deliver the sound information.
And the source mentioned that typical commercial CIs, they operate within a specific range for that number.
They do. Usually they have somewhere between 12 and 22 electrodes. That's the common range.
Okay.
But the simulator lets you play around with that, even go beyond it. It goes up to 40, actually.
Wow, okay, so you can see the difference.
Exactly. And what's really fascinating is just watching how the visual representation of the sound changes as you increase or decrease that number.
So fewer electrodes means a much rougher picture of the sound.
Pretty much. A coarser representation. More electrodes allow for greater frequency detail to be captured and transmitted.
More fine-grained information.
Right. The source really highlights how much fidelity you gain or lose just depending on how many channels are processing that incoming sound. Makes that whole simplification process really obvious visually.
Yeah, I could see how that would work. It really visualizes how that sound information gets, like, parceled out. What about the spectrogram chart, the one on the left? That's controls too.
Yeah. That's maybe less about the core CI process itself and more about how you're visualizing the incoming sound before it gets processed.
Okay, how so?
Well, autoscale adjusts the frequency chart's sensitivity kind of dynamically. It zooms in, basically. Useful for seeing quieter sounds in detail.
Right.
Fixed scale, on the other hand, gives you a consistent range based on the maximum possible volume it might encounter.
So softer sounds might get lost visually.
They might be harder to distinguish, yeah. But it gives you a stable reference point. They're just different ways to look at the intensity, the loudness across different frequencies.
Fascinating stuff. And the source material, it even hints at where this kind of simulation, or maybe CI tech itself, might go next.
It does, yeah. It mentions potential features they could add to the simulator down the line.
Like what?
Things like simulating current spread. That's a real challenge in actual CIs.
What is current spread?
It's where the electrical field from one electrode can sort of bleed over and stimulate the nerve fibers meant for nearby electrodes.
Ah, causing interference.
Basically, yeah. Simulating that would show why getting clear separation between channels is so important. Or maybe adding a noise gate to help filter out background noise.
Practical improvements.
These things point towards the ongoing efforts to, refine the signal that the auditory nerve actually gets. Make it cleaner, more distinct.
And they even mention electrode counts beyond what's typical now.
Absolutely. While this simulator goes up to 40, The source notes that research trials have used arrays with even more, up to 48 electrodes sometimes.
So the push is always for more information capacity.
It definitely reflects that continuous drive to pack more detail, more information into that electrical signal, trying to get closer to the richness of natural hearing.
So what does this all really boil down to for you, the listener?
Yeah.
Well, this simulator, it shows us in a really powerful visual way how complex sound gets broken down.
Converted into a much simpler pattern.
Yeah, a simpler pattern of electrical signals delivered through a, frankly, limited number of points, those electrodes.
Right. And we saw you can change layouts, visualization scales.
But crucially, playing with that electrode number, that immediately shows you how more channels capture more frequency detail. You get a finer representation of the sound.
And we know typical implants sit around 12 to 22, generally.
But research is pushing past that.
Constantly. The tool makes it really clear that a CI isn't just hearing, it's creating a sophisticated representation of sound for the brain, built from these electrical patterns.
And that, I think, leaves us with a pretty incredible thought to ponder. When you really consider how this simulation, and by extension, a real CI, takes the vast, continuous, incredibly complex information of sound and has to reduce it, condense it down to discrete electrical pulses delivered through maybe just, 16, 20, perhaps 40 points.
Compared to the millions of hair cells in a healthy cochlea, yeah.
Exactly. What does that stark difference tell us about the sheer, almost breathtaking complexity of our natural hearing?
It's staggering.
And also, what does it reveal about the immense challenge technologically, biologically, of trying to replicate that experience electrically?
It's a huge undertaking.
So just take a moment and try to imagine, how might different sounds we do, maybe a familiar voice or a complex piece of music, or even just leaves rustling, how might those sounds be represented by those blinking patterns with, say, just 8 electrodes versus 22 or even 40? It really makes you think.
Yeah.
Yeah, very nice, very nice. I couldn't have done any better. And I have PhD in cochlear implants. So good luck to all humans out there. Very nice, very nice. Okay, shall we move on? This is deployed. I forgot the. I think now I understand the question that someone asked. Can you add option which would open our page when clicked on it? For example, contact add testimonials. Yeah, it's a good reminder. Yeah, thank you for that. And that's a standard page we always have, yeah, and we forgot about it. Yeah, we'll have a home, about contact, a button, overview. We want to add this audio description because it's so good to the page as well. So it's just available on the site. Later we'll be embedding a YouTube video as well onto the page. Well, this is us actually making it. So what do we need to do? What do we need to do? What do we need to do? where it's getting a information from. Not sure. Meant to be getting information from. Okay, this is a good example. Don't quite understand why can't it pull. What if you have them side by side? No. Yeah, the other thing we have starting for our own for the whole website, but I'm not sure if we can use it in this case because it has all that Tailwind CSS stuff. So it might interfere with it. It might interfere with it. Hey, can you add the rest of this script based on the example provided below? It needs to be adjusted for the content of this specific page. Oh, come on, don't send it. Don't send it. So we need the sample. Okay, did it actually do correct job? Yes, it did. Okay, this is the boring bit. Sorry for that. Image, we need an image for it. We have an image for it. This one actually has colors in it. This one has colors in it. get the array. How many turns normally a cochlea? How many? How many? How many? How many turns normal cochlea has? Should be more than that. Hey, don't change the code yet, just explain. Yeah, 2.5, 2.75 turns. Is that even correct? Well, would be better than what it currently is. Okay, can we update the code, including the description at the bottom of the page? Can we? Is it because we are using the microphone over there? Can we update the code based on a correct number of turns in Cochlear, and also update the text discussion and the instructions at the bottom of the page? Also, another thing, a separate thing, can we add an option to choose color schemes? So we want to keep the current one as default, but we would also like to choose other color palette, like hot, rainbow, ocean, whatever other color palettes you can suggest. Let's see if this should be changing the code. Also, we need a better prompt engineer. We need a better prompt engineer. Can I in general replace Visual Studio Code with this and just use this as my development environment? I'm not sure. Well, I don't think so. Not yet. At least not yet. Okay, changed. Default green, ocean, sunrise, rainbow. Okay. I actually like it a lot. It's really nice. Very, very nice. If you like rainbow, follow the rainbow. Array type spiral linear. So linear is linear, spiral now has was it around 2.5 turns. That looks correct. I meant to know. I have a PhD in cochlear implants, so I should know, but yeah, I don't. And we can do up to well, right, with the when you have more electrodes, they would generally not be inserted to the same depth. So I'm not sure. Kind of like this though. Well, maybe they should. Okay, we have sunrise. Sunrise is nice. Love it. Ocean, ocean, ocean. Very nice. Love the ocean as well. A default green. Shall we leave that as default? Rainbow. Rainbow is good. Okay, we have the linear rainbow, spiral rainbow, any rainbow under the sun. Okay. You're getting a lot of views for these streams, but not much interaction. Unfortunately, or fortunately, well, I don't know. If you interact, you might not be as nice. I don't know. But generally, the streams are there for you to, yes, interact. And if we don't have a human, we'll give it to the robots. Robots. What else would you change? I think we've been stuck on this one for too long, have we? Or are there any other substantial improvements we can make? The reason we still need the Visual Studio Code is because we need to like fine-tune the code before putting it in production. Yeah. Before putting it in production. Can actually ask the bot if it's ready for production. Do you think it's ready for production? It's 400 lines. Ooh, 450 lines. That's the color business and other business. Hey, can you update the code based on the example provided above?
Technology that feels almost like science fiction, the Cochlear implant.
Yeah, fascinating stuff. And we're looking at it through a particular lens today using this online simulator that aims to show how
Made
it all works.
changes.
Right, so our mission
Made changes. Made changes.
Yeah, we need this code ready for production. Production. Okay, there's no humans who like to chat. Let's bring a prompt engineer. Whatever, engineer. Header. We need a header. Header. And yes, we have ads on this site. I used to apologize for that, but not sure why. Why are we apologizing? I don't know. And let's see if it's ready for. So when you paste code in here, how many lines is it now? 4, 5, 8. It should be 491. Okay, that looks correct. Let's actually change. What's the problem? No, that's fine. That error is actually okay, I think. Hey, can you look at the code and let me know if it's ready for product? Can you? What? Can you? What the? Is something taking up the mic? Well, I know what it is, but we needed to be able to talk to it. Hey, can you let go over this code and let me know if it's ready for production? So we're just after any major problems that this code might have. It can be highly critical is fine. Okay, what's the development agent currently doing?
I see. The development agent is reviewing a document on the left side of the screen, and there's also code being displayed on the right side. The agent made changes to the code on the right side, specifically in the Cochlear simulator file. It looks like it updated the part related to the microphone access in the simulation process. Sure. The developer is suggesting a few improvements. They mentioned enhancing the real-world audio processing by adding a noise gate and improving the simulation for the electrodes. They also suggest improving the user interface by adding frequency labels, a pause-resume button, and different color options. Additionally, they recommend adding preloaded audio samples for better demonstration. Sure. First, the developer suggests improving the real-world audio processing by adding a noise gate to reduce low-level background noise. Second, they recommend simulating the current spread for the electrodes to make the visualization more realistic. Third, they suggest improving the user interface with frequency labels, a pause and resume button, and more color options. Finally, they propose adding preloaded audio samples for better testing and demonstration. Sure. The developer identified 4 critical issues. First, there are broken asset links in the file structure, which can cause problems when deploying. Second, there are potential conflicts with the Tailwind CSS styling. Third, there's a global JavaScript scope issue that could lead to conflicts. And fourth, there's a problem with the initial canvas rendering that might cause delays or display issues. The most critical issue would be addressing the broken asset links, since that can prevent the application from working properly in production. After fixing that, tackling the canvas rendering issue would be important to ensure a smooth user experience. The agent is now reviewing an updated response from the developer, which includes the fixes and improvements that were suggested. It seems to be checking the updated code and the changes that were implemented. The agent is now examining the code changes, specifically in the Cochlear simulator layout file, focusing on the implementation of the corrected asset links and the adjustments to the user interface elements. The code in the Cochlear simulator file is mainly responsible for the visualization of the Cochlear simulation, including the spiral graph and the spectrogram. It handles the microphone input, processes the audio, and updates the display accordingly. Some parts, like the initial canvas rendering setup with the timeout, might be optimized for production to ensure smoother performance and reliability.
You should ask the developer to perform a final review to ensure that all the critical issues have been addressed and that the code is ready for production. You can also ask them to verify that the implemented changes are working correctly and that there are no new issues introduced. Additionally, confirming that the code follows best practices is important for maintainability. The developer is currently assessing the production readiness of the application. They are verifying that all previously flagged critical issues have been addressed, and they're documenting the process to ensure production readiness. They are also reviewing the code for robustness and confirming that the new features are working correctly. They are stating that the critical issues have been fixed, the asset links are resolved, the JavaScript code is encapsulated, and the canvas rendering is fixed. They also confirm that the added features, like the spiral graph and color scheme, are working correctly. They conclude by saying that the version is now ready for production. You should ask the developer to implement a noise gate in the audio processing filter, out the low-level background noise. This will ensure that the spectrogram only shows the relevant sounds, providing a cleaner visualization for the user. Remind them that this was one of their suggested improvements for enhanced audio processing. The developer is now addressing the suggestion for implementing a noise gate. They are considering the technical feasibility and explaining how it can enhance the user experience by filtering out low-level background noise. They are also discussing the best way to integrate this feature into the simulator. The developer is now providing an update on the implementation of the noise gate. They have added the noise gate control, updated the audio processing logic, and provided explanations in the code comments. They are showing the updated code and confirming that the feature is working as expected. It might be better to have the noise control as an option for the user to enable or disable, rather than having it on by default. This would allow users to customize their experience depending on their audio environment and preferences. Based on the visual feedback on the screen, it appears that the noise gate control might not be functioning as expected. The spectrogram doesn't appear to show a significant difference when toggling the noise gate on or off. It might be necessary for the developer to review the code for the noise gate and ensure that it is correctly filtering the audio input. The developer is evaluating the noise gate implementation, and they've realized that the current threshold-based approach isn't effective. They are now planning to improve the noise gate by calculating the average audio level and using that as a dynamic threshold. They believe this will provide a more effective and accurate noise gating. The developer is explaining that the current noise gating implementation is primarily affecting low-frequency noise, such as humming or background sounds, like fans. They are describing how the updated algorithm will calculate the average audio level across all frequencies to create a more effective noise gate that can handle a wider range of sounds. Based on the visual information on the screen and your observation that there's no difference, it appears that the updated noise gate implementation might not be working correctly. The spectrogram should show a noticeable difference when the noise gate is enabled, especially with background noise. It might be necessary for the developer to further debug the code and ensure that the dynamic threshold is being applied correctly. The developer acknowledges that the previous noise gate implementation was not effective. They have now updated the code to use a more effective method that calculates the average audio level to dynamically set the noise gate threshold. They confirm that this new approach provides a more responsive and accurate noise gating, which should result in a clearer visualization when the noise gate is enabled. If the noise gate is working correctly, you should see a clear reduction in the spectrogram when background noise is present and the noise gate is enabled. The low-frequency noise should be significantly filtered out or eliminated, making the sounds of interest clearer on the visualization. Based on your description and the visual feedback, it seems that the noise gate functionality is still not working as expected, despite the recent updates. You are not seeing the intended reduction in background noise in the spectrogram. The developer may need to further investigate the code and ensure that the noise gating process is correctly applied to the audio signal. It does seem like we're going around in circles trying to get that noise gate working properly. The developer is focusing on refining the threshold and making sure the dynamic adjustment works correctly. They're trying different approaches to ensure the noise gate effectively filters out background noise without affecting the desired sounds. Hopefully soon they'll crack the code and it will work like a charm. Based on the updates from the developer, they are continuing to refine and debug the noise gate functionality. They are focusing on adjusting the threshold algorithm and ensuring that it properly differentiates between background noise and desired sounds. They are working to make sure the noise gate effectively reduces unwanted noise without compromising the clarity of the main audio.
Okay, so now we have a threshold as well. So the problem I was saying is that we have this noise like humming from a desktop. Okay, it went away. Okay, if we can change the threshold as well. Threshold, Mueller, 1, 2, 1, 2. So you see that noise there when I'm not talking. In theory, when you increase the threshold, that should go away. Okay, it actually does. 1, 1, 1, 1, 1, 1, 1, 1. It's actually, I think it actually works. Okay, I think it actually works. Can we update the text at the bottom of the page? Include the description of what the noise gate is doing and how the threshold works. And yeah, I think currently it's disabled by default. Just, yeah, so you only use it if you have too much noise in the room, kind of thing. And also can we somehow try and improve the layout of the canvas of the simulation? Ideally, yeah, everything will appear on one screen really well, regardless of the screen size. Can we do all that? Yeah, we're having a lot of traffic on the stream, like almost 400 views, but not much engagement. So yeah, if you have any questions, comments, eventually what we make here goes onto this website. You can already check it out. We're just trying to improve it a bit, make it production ready. But essentially everything is up there on BioniChaos.com. So go check it out. Leave your feedback, comments, complaints, anything you like. Yes, we're currently doing hearing, but we're covering other topics as well: cardiovascular, ECG, PPG, neurological stuff, EEG mainly, other neurological things, devices, clinical research, implantable, yeah, any biomedical data. And we were even making some games. So you can, yeah, this is all the topics we cover: neurological, cardio, biomedical imaging. Yep, there's not much there. Actually, there should be more. I actually change how the landing page, how the search works, how this drop-down window works. So I have to update that. We have stuff on vision, including this webcam filter that I'm currently using. It's funny that I really lose audience when I'm talking. But when when AI is talking, either Notebook LM or the prompt engineer that we have, I get way more traffic on the get way more traffic. So I don't know, what does that tell you? I can't even do the human stuff, even the humane things. The robot still does them better. Anyway, we have vision, hearing. Obviously, currently we're touching on hearing. We have this Cochlear simulator that we're working on currently. We also have a cochlear implant insertion simulator that you can try out. This one is actually 3D. You can scroll, measure your forces, depth, force, speed of insertion, so you can play surgeon. If your parents ever wanted you to become a surgeon, well, this is your opportunity. And after using this tool, you can tell them you are a surgeon. Just a web surgeon. A web surgeon. So you can play around with this, learn about cochlear implants, listen to professional podcasters talking about this. Adding Notebook LM now on pretty much every page for your convenience. Yes, we got 300 views on this stream, but not much interaction. Not sure why. Can you quickly describe what the developer agent was doing to the code and what changes it made?
The developer agent updated the text at the bottom of the page to explain the new noise gate feature. It added details about how the checkbox and threshold slider work together to filter out background noise. Yes, the developer adjusted the layout so that all the interactive components fit on a single screen, eliminating the need to scroll. They also ensured that the text flows naturally below the simulator. The future directions mention incorporating more advanced concepts, such as simulating current spread and exploring different electrode arrays to study how sound is represented in cochlear implants. This tool is a cochlear simulator that allows users to explore different settings for cochlear implants, such as the array type, number of electrodes, and color scheme. It also includes a noise gate feature to filter out background noise. For improvements, perhaps adding more advanced features like simulating different types of sounds or providing more detailed explanations of the parameters could enhance the tool's functionality. Yes, it's possible to rearrange the layout. You could place the Enable checkbox and the Threshold slider on the same line within the Control section, especially on wider screens, to make it more compact and user-friendly. The developer is restructuring the control layout specifically for the noise gate components. They're regrouping the Enable checkbox and the Threshold slider into a single container using Flexbox to achieve a more compact and organized layout, especially on larger screens. They also reconfigured the main grid layout to be a 3x2 structure, which improves the overall balance and readability of the controls, making the interface more user-friendly across different screen sizes. Yes, the developer stated that the new layout will still display all the interactive components within the single screen, maintaining the improved layout from before. Absolutely. Everything we're working on with these simulators is part of a larger project on BioniChaos.com. It's a fantastic resource with various interactive tools for biomedical engineering and neuroscience. We encourage you to visit the website and explore the different simulators and resources available. If you visit the Bionic Chaos website and explore the tools there, you might even find opportunities to earn certificates for your engagement. It's a great way to learn and get recognized for your interest in the field. Oh, I understand. So, the idea of getting a certificate was just a fun suggestion. It's still a great resource to explore for learning about biomedical engineering. And don't forget to hit that like button if you would find the simulators helpful. It's a great way to show your support. It seems like the improvements have made the layout more compact and user-friendly. If all the functionalities are working correctly and the design meets the requirements, it could be considered ready for production. And if anyone specializing in cochlear implants is watching, your detailed feedback on this simulator would be incredibly valuable. Please feel free to share your thoughts and suggestions. Given the focus on cochlear implants, relevant simulations could include exploring different electrode placements and their impact on sound perception, or simulating the effects of varying parameters like frequency channels and stimulation in levels. Additionally, simulations demonstrating how noise reduction strategies work could be very insightful.
Okay, let's unpack this. We are diving into the really fascinating world of cochlear implants today. We're using a description of an online simulator someone shared as our guide. Think of it as giving us a kind of keyhole view into how these, well, incredible devices process sound.
Exactly. That's the mission for this deep dive. We'll use the source material on this simulator to really try and grasp the core principles, how a cochlear implant actually works.
Seeing how those complex sound waves get translated.
Or maybe engineered is a better word.
Re-engineered, yeah. Into electrical signals the brain can hopefully interpret.
Right.
And that re-engineering aspect is so crucial, isn't it? It's not like a hearing aid just turning up the volume.
No, not at all. CIs are neuroprosthetics.
They completely bypass damaged parts of the ear.
The outer, the middle ear, yeah. They send signals straight to the auditory nerve.
It's just a fundamentally different way of handling sound.
Totally different.
So let's look at what this simulator actually shows us. The source says it takes audio from a microphone and visualizes its complexity, but also its simplification.
And that's what's so revealing, I think. You can see that simplification happening.
Mm-hmm.
And you can play with the controls that, influence it.
Right.
When you adjust things, you're basically changing how that raw sound gets prepped for the nerve.
Okay. So what parameters can you actually tweak? The source mentions array type, letting you visualize the electrodes either in a spiral pattern, mimicking the cochlea shape, those 2.5 turns.
Right, trying to reflect the anatomy.
Or just a basic linear layout.
And those visualizations, they tie into how much information can actually get through, right? It brings up that big question the simulator helps you explore. Just how much detail can these devices realistically convey?
And that's where the electrodes come in.
Exactly. The number of electrodes control. That's critical.
Ah, right. The source points out pretty clearly more electrodes mean more frequency detail.
Generally, yes. Which usually translates to better perception, understanding speech, maybe appreciating music more.
Better clarity.
Precisely. So the simulator lets you see sound mapped across, I think it goes up to 40 electrodes.
40, yeah.
Now, put that in context. A healthy human ear has thousands of tiny hair cells, each tuned to a slightly different frequency. Incredible detail.
Wow. Thousands versus 40.
It really highlights how much the CI system has to, compress and prioritize that sound information to fit it onto this limited number of channels. And the source even mentions research pushing for more, like 48 electrodes. It's this constant quest for more detail, more nuance.
So when you change that number in the simulator,
you can actually see it. You see how the fine-grained frequency information gets sort of smudged together when you have fewer electrodes. That's the simplification process right there. Visualize.
Yeah, that makes a lot of sense. Like trying to show a detailed picture with just a few big blocks of color instead of tiny pixels.
Good analogy. More pixels or electrodes means a potentially clearer picture.
Okay, but what about the real world? Noisy cafes, traffic, how does it handle background noise?
Well, that's exactly what the noise gate control is for. It's pretty vital in noisy places.
How does that work?
You switch it on, and then you set a threshold. The simulator shows how this acts like a filter. Sounds below that threshold just get, digitally filtered out. It tries to isolate the louder sounds, the ones you probably want to hear from the background hum.
Like ignoring the quiet chatter to focus on the person talking to you?
Something like that, yeah. And the source notes an interesting little detail here. If you don't use the noise gate, you might see this constant little bar of activity way over on the left of the visualization.
What's that?
It's not actual environmental noise. It's apparently a low-level artifact from the microphone itself.
Oh, interesting.
Yeah, it just shows how much processing happens even before the signal gets near the brain.
Wow. Okay. And there are other controls too, right? Like spectrogram, y-axis, scale, color scheme.
Yeah, those sound more like user preferences, ways to view the data rather than changing the core processing itself. Visual aids, basically.
Yeah. Makes sense.
But, connecting this to the bigger picture, the source material does hint at some really fascinating future directions for simulators like this one.
Oh, like what?
Well, potentially modeling things like current spread.
Current spread. What exactly is that?
Okay, think of it like signal leakage. When you activate one electrode, the electrical signal isn't perfectly contained. Some of it can spread and stimulate nerve fibers nearby, fibers that were meant for other electrodes.
Ah, so it blurs the signal a bit.
Exactly. It can blur the lines between those frequency channels. It impacts channel separation, which affects the overall clarity. Simulators that could show that effect could be super powerful tools for researchers, designing better implants, better signal strategies.
I could see that.
And also the idea of using preloaded audio samples, which the source mentions. Imagine consistently testing how, say, a specific consonant sound or musical chord gets represented with different settings.
Yeah, for standardized comparisons.
Okay.
So wrapping this up, what does exploring a simulator like this really mean for you, the listener? It offers this really compelling visual glimpse into how something that feels so seamless, if you have typical hearing, has to be fundamentally re-engineered, compressed, simplified by a CI, just to begin its journey to the brain.
And considering that level of processing, the inherent limitations you can see even in a simplified model like this, it really raises an interesting question for you to maybe ponder after this deep dive. How might understanding this technological translation of complex sound change the way you think about your own perception of the sounds all around you, regardless of how you hear? You can play with the controls that, influence it.
Right.
When you adjust things, you're basically changing how that raw sound gets prepped for the nerve.
Okay.
lost that DJ. We lost that DJ. So I have this interactive EEG brainwave simulator. It's working fine. We have two versions of it. One is more advanced. One is more advanced. We'll pop those as images for Gemini. Gemini. And let it run, because we had good luck with it before. So 3 images for a web application. Let it run, see what it gives us. Okay, meant to turn the canvas. We meant to turn the canvas. We meant to turn the canvas. Oops. So canvas is on. Go, Gemini, go. Okay. Mueller. Okay, I don't know if you like the DJ or not. Shall we keep using it? Perhaps not. It's annoying that it stops after some time. I don't know why. Yeah, and most of our time it's quite painful to listen to. A bit painful to listen to. Okay, it made an application. Don't particularly like it. Can we somehow make the layout better so that, for example, on wider screens we have the controls on the left? No, he actually did do it. On a vertical smaller screen. Can we show? Anyway, can you suggest any improvements to the application? Okay, it's actually working. I think it's actually working. It's actually quite nice. I like the idea. Where's the control for the bandwidth? What? Okay, might need a prompt engineer. We might need the prompt engineer. Okay, so can we what the
Of course, the application is an advanced EEG signal simulator. It's designed to help users interactively explore brainwave characteristics, common artifacts, and the impact of real-world signal artifacts. On the left side, you can see controls for brain state presets, like focus concentration, and artifact simulation, where you can adjust the intensity of muscle and eye blink artifacts. There are also fine-tuned controls for different brainwave frequencies, like delta, theta, alpha, and beta, allowing you to adjust their amplitude. On the right side, you can see two main graphs: the power spectrum frequency domain, which shows the frequency components and their intensity, and the simulated waveform time domain, which displays the actual waveform over time. You can modify the various settings and see the effects reflected in the graphs in real time. It's a visual and interactive way to understand how different brainwave components and artifacts contribute to the overall EEG signal. The de- Okay, I can address the developer regarding the bandwidth settings. Developer, could you please check the implementation of the bandwidth controls in the fine-tune control section? The user mentioned that while they can adjust the frequency and amplitude, there might be an issue with accurately controlling the bandwidth. Please ensure that the bandwidth settings are correctly reflected in the simulated signal and the power spectrum. Thank you. The developer has identified the issue with the bandwidth control. They explain that the current function generates pure sine waves without considering bandwidth, which causes the inaccurate results. They're planning to create a new function to integrate bandwidth control properly, allowing the user to adjust the shape of the wave. They will then test the updated solution to ensure it works correctly. The developer has implemented a new function called Generate Bandwidth to address the bandwidth issue. This function generates the signal by summing multiple sine waves with frequencies distributed across the specified bandwidth. This creates a more realistic brainwave signal and ensures that the power spectrum graph accurately reflects the bandwidth setting. They have corrected the code, and the user should now be able to see the changes reflected in the signal and the graph. Developer, the user confirms that the bandwidth control is now working correctly. However, they have a couple more requests. Could you please double-check the entire codebase to ensure there are no other issues? Also, when the page loads, could the spectrum overlays for delta, theta, alpha, and beta waves be set to be selected by default? The user wants these overlays to be visible by default. Additionally, they noticed something unusual with the signal spectrum and would like you to double-check how that is being generated. Thank you for your attention to these details. Developer, the user would like to make changes to the simulated EEG waveform in the time domain graph. They would like you to remove the decimal points on the y-axis and extend the time period displayed on the x-axis to 5 seconds. Please apply these changes to the graph. Thank you for your assistance. I understand. You'd like to keep the time period at 5 seconds and remove the decimal points on the y-axis of the simulated EEG waveform graph. I will relay that request to the developer. The developer is currently performing a thorough code review of the EEG simulator. They are scrutinizing the code base
Okay, welcome back to the deep dive. We've got a really interesting stack of material here today. Screenshots, dev notes, code logs, all pointing towards the development journey of this advanced EEG signal simulator.
Yeah, this looks fascinating. It's like a peek behind the curtain, isn't it?
Yeah.
How these complex tools actually get made.
Exactly.
So based on what you've got here, our mission basically is to unpack that whole process from, the initial idea, maybe sparked by those pictures,
Right.
right through the challenges and the refinements that eventually brought this simulator to life.
Precisely. Because, when you hear simulating brainwaves, it sounds maybe simple, but copying these complex biological signals, EEG, it's way more than just drawing weighty lines.
Oh, definitely.
You're trying to capture these really intricate patterns, deal with all the messy stuff from the real world, like artifacts,
Noise and things.
and solve some honestly quite subtle technical puzzles along the way.
It's a great example, I think, of how much engineering can be sort of hidden under a simple-looking interface.
Totally. So looking at the very start in these sources, the initial goal seems pretty clear. Take those visual concepts, the layouts and the images,
Right.
and just turn them into a working interactive simulator, something that feels responsive, like you're actually controlling something.
Building directly from that visual, yeah. And the core functions they planned from the start, it looks like they centered around controlling that simulated signal. So having presets for different brain states, simulating artifacts, muscle twitches, eye blinks, stuff that messes up real EVG.
Yeah, the EMG, EOG things.
Exactly. And also giving users control over the actual brainwave parameters themselves.
And the tech stack, how did they decide to build it? The notes say pretty standard web stuff, HTML, CSS.
Looks like Tailwind CSS got a mention for styling.
Yeah, Tailwind specifically, and then JavaScript doing, well, all the heavy lifting, the logic, generating signals, updating everything in real time.
Makes sense. And that first version, it already had some, solid basic features. You can adjust the power, the amplitude, basically, of the main brain waves.
Delta, theta, alpha, beta.
Right, using simple sliders.
Yeah.
Very familiar interface.
Classic sliders, yeah. Super easy for a quick tweak. And I see you could also pick predefined states like relaxed or focused.
Which presumably just set those sliders to, typical patterns for those mental states.
Makes sense.
And crucially, right from the beginning, you could see the output in two really essential ways for signal analysis.
Okay.
The time domain, that's your classic squiggly line graph, amplitude over time.
The waveform.
And the frequency domain, using a power spectrum graph, that shows you how much of each frequency is actually in the signal.
Essential for EEG analysis. And a smart touch noted early on was being able to toggle these ideal spectrum overlays on the frequency graph.
Yeah, I saw that.
So you could see what a pure frequency band should look like. Helps you guide your adjustments, gives you a reference point.
That's a really good feature for learning or calibration. Okay, so now this is where it gets interesting, where development becomes iterative, right? Shaped by feedback. The notes show a request came in pretty quickly. Users needed more advanced controls, more precise controls for fine-tuning the waves.
Yeah, because sliders are great for a general feel, but if you're trying to recreate something really specific or run detailed experiments...
You need numbers, precision.
Exactly.
Absolutely.
Yeah.
So the focus shifted to implementing that. The fine-tune waves section, which started with just those sliders. They made it switchable, defaulted to simple, but you could toggle it to an advanced view.
And that advanced view, looking at the sources, it had, like the example image showed, these precise numeric input fields.
Right.
Frequency in hertz, bandwidth, amplitude as a percentage for each wave type.
No more guessing with a slider. You could type in the exact values you want.
Much more powerful.
But, implementing this wasn't just a simple UI change. The underlying code, the signal generation, the spectrum analysis...
That all had to get smarter, more sophisticated to actually handle these precise numeric parameters accurately.
Right. The engine needed an upgrade.
Yeah.
Okay, so they add these great precise controls.
Yeah.
Then what happens? As often happens in development.
Yep. A bug surfaces.
A key bug. The logs mention a user reporting that the bandwidth control, it just didn't seem to be doing what they expected.
And this really highlights why user testing is so critical, doesn't it? Because that bandwidth control is vital for making the simulation realistic.
How so?
Well, it doesn't just set the center frequency of a wave, like alpha at 10 hertz. It determines the spread of frequencies around that center. Real brain signals aren't perfect, single frequency tones. They're messy, they occupy a band of frequencies, bandwidth controls that spread.
Got it. So they had to investigate.
They did, confirm the issue. And by digging into the code, specifically that generate composite signal function,
They found the core problem. And here's the crucial part.
Okay.
The simulator was generating pure single-frequency sine waves for each wave type. It was completely ignoring the bandwidth setting when it actually created the signal.
Wait, so the ideal overlays, the visual guides,
Those were using the bandwidth setting correctly, showing the right shape.
but the actual signal being generated and plotted didn't use that bandwidth info at all.
Exactly, a total disconnect. The ideal graphs looked right, showing the spread, but the simulated signal itself was just a mix of pure tones.
Wow.
So the consequence was, when you adjusted the bandwidth slider or input, the actual power spectrum graph, the one generated from the signal, it didn't change shapes. It just showed those sharp single-frequency peaks.
Okay, that's a pretty fundamental flaw for an EEG simulator. Subtle, but critical. So how did they fix it? How do you actually simulate bandwidth properly?
Well, they had to ditch that simple single sine wave approach. Replace it with something that could create a signal that genuinely has bandwidth.
Makes sense.
This led them to create a new function, and they named it better too, generate bandwave.
Generate bandwave. The name says it all.
Pretty much. Instead of just one sine wave at the center frequency, this new function builds the signal by summing up multiple sine waves
Okay.
with frequencies that are deliberately spread out across the specified bandwidth range.
So it's like building up that spread by combining lots of little waves within that frequency band. Is that the idea?
That's the basic principle, yeah. The notes mention they use a simple noise band approximation method. It's a common technique to simulate a band of frequencies instead of just one perfect tone.
Right.
And this change was absolutely key. It meant the main power spectrum graph finally started to accurately reflect the bandwidth setting the user chose.
So the simulation became much more true to life, much closer to real brain signals.
Exactly. A much more realistic simulation overall.
Okay, so with that major simulation bug squashed, the final bits in the sources seem to focus on, like, polishing things up, user experience, verification.
Yes, exactly. A few quality of life improvements based on user feedback, just to refine the interface.
What were some of those specific UI tweaks they made?
Well, looking at the notes and screenshots, one change was making those spectrum overlays for delta, theta, alpha, beta enabled by default when the page loads.
So you see the ideal guides straight away?
Yeah, it gives you media visual context without having to click anything.
Sure. What else?
They also tidied up the y-axis on the time domain waveform graph, adjusted it so it only shows whole integer values.
Oh, just for neatness.
Pretty much. It's a small thing, but it makes the plot look cleaner, less cluttered.
And the x-axis, the time axis.
That got extended too, yeah.
Yeah.
The time domain graph now shows the full 5 seconds of simulated data. Gives you a wider view of the signal's behavior over time.
Okay, broader perspective. Now, there was also that note about a user thinking the signal spectrum generation looked unusual. How did they handle that?
Right, that query. They basically performed a thorough verification step.
Checking their math.
Essentially, yes. They re-examined the core calculations, specifically the FFT, the fast Fourier transform, which is the standard math tool to get from the time domain to the frequency domain, and also the power spectrum calculations themselves. The notes even mention checking the magnitude, effective resulti, and a sample scintillation specifically.
And what was the verdict? Was it unusual?
Nope. They confirm the calculations are correct and completely standard practice. FF result is just the FFT output, and a sample is the number of data points. The math was sound.
So the user's perception, maybe it was influenced by the old bandwidth bug?
That seems likely, yeah. The spectrum did look unusual before the fix because it wasn't showing bandwidth properly. But the underlying transformation math was correct all along.
Okay, that makes sense. And the devlogs show a final code review after all this.
Yeah, a thorough review, which is, essential best practice after making significant changes like fixing that bandwidth bug, make sure everything holds together, no new issues introduced.
Absolutely. Wow. So this deep dive really took us on quite the ride, didn't it? Through the whole life cycle of building this simulator.
Certainly.
From, translating that initial visual concept into something real, adding those layers of precise control, then hitting that fundamental simulation bug with the bandwidth.
Crucial find.
Fixing it, and finally polishing the interface based on how people were actually using it.
It's such a clear illustration of the complexity that can hide behind what looks like a simple tool.
Yeah.
And it really underlines how important accurate underlying models are, right?
Yeah.
Like making sure you're truly simulating bandwidth, not just drawing a picture of it, if you want the tool to be genuinely useful and realistic.
And it shows how building stuff like this is almost never a straight path. It's iterative. You build, you get feedback, you find unexpected problems.
You solve them, you refine.
Yeah.
It's a cycle.
Thinking about this for, anyone listening, building anything complex, it often involves that same process, doesn't it? Breaking it down, adding detail, hitting snags you didn't expect, and then tweaking based on how it actually performs or how it gets used.
It really feels like a universal pattern. Software, research projects, even just learning a new skill, maybe.
Yeah, absolutely. Okay, so here's a final thought to leave everyone with, kind of building on all this.
Okay.
If simulating just the electrical signals of brainwaves needs this much detailed attention to frequency, bandwidth, artifacts, the precise math underneath, what does that complexity suggest about the immense challenges and maybe the modeling or simulating even more complex aspects of us, things like consciousness, perception, abstract thought?
That's a big question. Definitely something to ponder as you look at your own complex data or system.
By the way, as per usual, go check out the website. Everything we do eventually appears on the site. BioniChaos.com, so you can scroll through the topics that you like: hearing, neuro, cardio, imaging, vision, hearing, EMG, electromyography. There's even games as well. And check the website. Let us know what you think. We can address your questions, comments, complaints. Welcome as well. And don't forget to smash that like button, subscribe, unsubscribe. You know what to do. And we're also making advanced EEG signal simulator. Actually, I had to redo it. So it brought to you by Google Gemini.
Welcome to the deep dive. Today we're digging into some source material you sent over about brainwave signals. Specifically, there's this simulator.
That's right. And the real puzzle, the core question, seems to be about what we're seeing in the simulator's output. You've got this solid blue line, the signal spectrum.
Right.
And then there's that dotted red line, the ideal delta. They look, related somehow, but they're definitely not the same shape.
Exactly. And that difference, that mismatch, is what we're going to unpack today based on the sources. So our mission, figure out why those two lines aren't lining up in the simulation.
Okay, let's do it. So the source material actually gives us a pretty good analogy for the blue line, that signal spectrum. It calls it the cocktail.
The cocktail, like the final drink after you've mixed everything together.
Precisely. Yeah. This blue spectrum, it's the end result. It's what you get when you analyze the combined signal. And the ingredients in this particular cocktail, according to the sources, are, the brainwaves themselves, delta, theta, alpha, beta, but also, and this is important, potential artifacts. Things that aren't brainwaves, like muscle activity, EMG they call it.
Right, EMG.
And eye blinks, EOG. Those get mixed in too, potentially.
Oh, okay. So it's not just the brain's electrical signals. It's sort of anything the simulation is set up to include, electrically speaking. The source mentioned this this function idea, like generate composite signal.
Yeah, that's a good way to think about it programmatically.
Where you literally add up all those signals, the delta, the theta, the artifacts, point by point, creating one messy composite wave.
Yeah.
Then you run the analysis on that complex wave.
Exactly right. And the blue area on that plot shows you how the energy or power of that total combined signal spreads out across the different frequencies. Slow to fast, it's the fingerprint of the whole mix.
Got it, got it. So that's the blue line, the complex reality. What about the dotted red line then? The ideal delta. The source called that the pure ingredient.
Yes. It's like looking at just the pure orange juice before it goes into the cocktail. This red line is purely theoretical. It's a mathematical curve showing what the spectrum would look like if, and this is a big if, if the only thing in the entire simulation was your specific delta wave, perfectly clean, no other brain waves, no artifacts, nothing else.
So it's like a platonic ideal of the delta spectrum in this context.
Pretty much. A clean hypothetical baseline for just that one component.
Okay, so blue is the messy mix, red is the pure delta. But still, you'd think the blue line, since it contains delta, would track the red line more closely. Why the big difference in shape?
Right, and that brings us to the key reason identified in the source, wave interference.
Okay, so the different waves don't just like sit next to each other politely in the mix, they actually interact.
Exactly, they bump into each other. When you add waves, their peaks and troughs can either line up or cancel out. The source talks about constructive and destructive interference.
Constructive. That's when, say, a peak from delta happens at the same time as a peak from theta. They add up, making the signal bigger right then.
Precisely. Stronger at that moment. And destructive interference is the flip side. If a peak from one wave meets a trough from another,
they kind of cancel each other out, at least partially. Makes the signal weaker there?
Exactly. So think about it. The composite signal, the one that generates the blue spectrum, is the result of all these waves, delta, theta, alpha, beta, plus the artifacts constantly adding and subtracting from each other over time, constructively, destructively. It's a dynamic process.
So the final waveform that gets analyzed is much more complex, much more jagged or varied than just the smooth, pure delta wave by itself.
Right, and when you take that complex, interfered with waveform and analyze its frequency content, you don't get the clean shape of the isolated delta wave, the red line. You get the blue shape, which has been pushed and pulled by all those other interacting components.
The overlay then really helps you see how all those other signals are, like distorting the picture away from that pure red line shape.
That's the idea. It shows the impact of the mix.
Okay, that makes a lot more sense now.
Yeah.
So to boil it down, the blue line is the messy, real-world-ish result of mixing and interference. The red line is the clean, theoretical, single ingredient.
You've got it. The mixed reality versus the pure component. And, this whole idea isn't just about brainwaves in a simulator.
Right. This applies much more broadly, doesn't it? Understanding how a complex result emerges from interacting parts. It's key in so many fields.
Absolutely. Anytime you're looking at complex systems, signals, you're likely seeing the result of some kind of interference or interaction between the underlying components.
It definitely makes you think differently about signals you encounter, maybe without even realizing it.
It does. So maybe a final thought for you to take away. What other real-world cocktails are out there? Mixtures of signals, or maybe even forces or influences where the final result we see hides or changes the nature of the pure ingredients because of how they interfere with each other? Something to keep an eye out for?
Okay, it's pretty perfect. If you have any lecturers or teachers in the audience, yeah, good luck. I'll start polishing up, reviewing my resume. Well, eventually, everyone will be working for AI anyhow, one way or another. But yeah, it's pretty amazing what it does. Okay. Okay, this discussion, can you edit? It's really good. Would love it. Can we edit somewhere in the text as a standalone discussion in the text below the simulation. And also, if you could, so we have a podcast just on that discussion, audio file. So if you can add the player somewhere next to the text, where the text is, where the relevant text is, and we'll add the player, we'll add the audio file to it when deploying this thing on a server. So because currently you don't have access to that audio, but just yeah, let me know if you know what I mean. We really need a prompt engineer, but we keep losing the prompt engineer. If you are a prompt engineer, same thing. Start looking for jobs. It's just a provocation, of course. We're just trying to increase engagement. Because you get a lot of people watching this. This specific video was viewed 460 times. You had a few comments from one person, assuming it's a person and not a robot. Well, the fact that I couldn't understand what they said probably means they are a person. So yeah, if you have any questions, if you check the site, if you haven't, you can do it right now. It only takes a short time. And this is what the website looks like. Go check it out. Let me know what you think. If you like to check like games, if you're not into, well, you're probably not in the right place if you're not into biomedical data science, but we do have some games for you as well. But yes, it's mainly brainwaves, heart rates, heart rhythms, imaging, vision, computer vision, biomedical vision. We're doing optical illusions as well. Those might be interesting as well. Yeah, data analysis stuff. What's called what? Data analysis, modeling. Research. No, knowledge graphs. Yeah, we have this graphit. We'll be redoing these things, by the way, with the new LLM models to make them better. It's fine that every time I talk or something, the number of viewers is dropping. Yeah, tells me you prefer notebook LM rather than a human, which is fine. I'll probably have the same preference as well. So
Welcome to reality. What about the dotted red? But still, you'd think the blue line, since it contains delta, would track the red line more closely. Welcome to a new deep dive. Today we're plunging into the fascinating world of brain signals.
Yeah, and we're using a source that describes a specific tool, an advanced EEG signal simulator.
Okay, so let's unpack this then. What's our goal here? What are we trying to figure out?
Well, the mission is really to get a handle on what these EEG signals actually are, how they're, put together from their basic parts.
And what gets in the way? Like noise and stuff.
Exactly. Interference. What messes up clean recordings. And critically, how a tool like this simulator we're looking at helps us learn about these really complex waveforms.
Because, I mean, think about it. Our brains are constantly going all this electrical activity.
Non-stop.
And being able to measure that, understand it, that seems absolutely key for insights into like different cognitive states, right? Or diagnosing neurological problems.
Or even just grasping general brain function on a deeper level. It's fundamental.
Right.
And that's really where a simulator like the one in our source comes into play. It lets us generate a synthetic signal.
Synthetic, like artificial.
Oh, yeah. Basically an artificially created waveform, but one that mimics the characteristics of real brain activity.
How does it do that?
Well, the source explains it lets you combine the fundamental brain waves, delta, theta, alpha, beta, and then, crucially, it lets you add in common types of noise, artifacts, they call them.
Artifacts. Okay,
Yeah.
so instead of just getting this like messy real-world recording,
Which can be really chaotic, yeah.
this tool lets you build the signal piece by piece. See the components.
Exactly. You can isolate things, see how they interact. So, whether you're just curious about this stuff or maybe you need to get the basics down quickly.
This deep dive should give you that foundation.
Right. And what's really interesting, as the source points out, is how this kind of tool serves, well, two main groups. For someone new to EEG, it's like an intuitive playground. You tweak things, see the results instantly, helps build that gut feeling for how it works.
Makes sense. Learn by doing.
But then for someone more experienced, maybe, say, an engineer developing signal processing algorithms, it's a reliable utility.
How so?
Because you have this controllable, predictable signal, you know exactly what went into it, so you can test your algorithms maybe for filtering out that noise we mentioned, or even for developing brain-computer interfaces.
Gotcha. A controlled test bed. So, based on the source, how is this thing actually structured? How does it work?
So it describes the application as being split, basically. Control panels on one side, where you set everything up, configure the signal, and visualizations on the other side, where you see the results. You change something in the controls.
And the graphs update immediately.
Dynamically, yeah. So on that control side, there are a few key sections that really help illustrate how we characterize brain signals. First, brain state presets.
Presets, like pre-configured settings.
Exactly. And this is super helpful because, as the source notes, different mental states tend to correlate with different patterns of brainwaves.
Oh, right. Like being relaxed versus focused.
Precisely. So you might select relaxed meditative, and the simulator automatically boosts the alpha wave amplitude that's typically strong, around 8 to 12 hertz when you're relaxed but awake. It's a quick way to see a representative signal for a known state.
Ah. Okay, so you don't have to manually guess what a relaxed brain signal looks like. It shows you a typical composition. That's pretty smart.
It really helps connect the states to the signals. And then there's the artifact simulation section. This is so important.
Why is that?
Because, and the source really emphasizes this, real-world EEG is almost always contaminated. You get electrical signals that aren't actually coming from the brain itself.
Right, like muscle movements.
Exactly. The simulator lets you dial in common ones. You can add muscle artifact, that's EMG signal. It shows up as high-frequency noise, kind of spiky, from things like clenching your jaw or even just scalp muscle tension.
Yeah, the source mentions those look like really fast, messy spikes in the data.
Oh, they can totally swamp the brain signals you're trying to see. And then there's eye blink artifact EOG. That shows up differently.
How so?
As large, slow wave spikes, usually below like 1 hertz. It happens because your eye itself has an electrical charge, a dipole, and when you blink, it moves, creating this big voltage shift.
Wow. So being able to simulate these, it really drives home why cleaning up real EEG data is such a big deal. You have to get rid of this stuff first.
Absolutely. It makes you appreciate just how complex those real recordings are and why signal processing is essential.
Okay, so beyond presets and artifacts, what else can you control?
Well, then you have the fine-tune waves control panel. This is where you get really granular. You can adjust the fundamental brainwave components individually.
The delta, theta, alpha, beta waves.
Yep, delta, usually 0.5 to 4 hertz, deep sleep territory. Theta, 4 to 8 hertz, think drowsiness, light sleep, sometimes creativity. Alpha, 8 to 12 hertz, that relaxed wakefulness we mentioned. And beta, 13 to 30 hertz for active thinking, being alert, focused.
And you can just adjust sliders for these.
There's a simple mode, yeah, with sliders to quickly change the relative strength, the amplitude of each band. Easy way to play around.
But the source mentioned a customize mode, too, for digging deeper.
Exactly. In customized mode, you can get really specific. You can set the precise center frequency for a waveband.
Okay.
The bandwidth, like how spread out the frequencies are around that center point, and of course, the amplitude or power for each one.
So you could try and replicate specific findings from a research paper or something.
Precisely. Or just explore how changing just one parameter, like bandwidth, affects the overall look of the signal and its spectrum. Very powerful for understanding the building blocks.
And there was something about spectrum overlays mentioned in the controls section, dotted lines.
Right. Those show up on the power spectrum graph, which we'll get to. These overlays represent the sort of theoretical ideal shape of each pure brainwave band you've configured, like the raw ingredient before mixing.
Okay, like the ideal alpha shape, the ideal beta shape.
Exactly. Which leads us nicely into the visualization side. Two main graphs are presented in the source.
Right.
First, the power spectrum. This one's shown in the frequency domain.
Frequency domain, meaning it shows frequencies, not time.
Correct. It's generated by applying a mathematical tool called a fast Fourier transform, an FFT, to the raw signal. Think of the FFT as deconstructing the complex signal that changes over time and showing you how much energy or power is packed into each specific frequency. So you see peaks where your dominant brainwaves are. It's absolutely crucial for seeing the underlying frequency components.
Got it. So it tells you what frequencies are strongest in the mix and the other graph.
That's the simulated EEG waveform. This one is in the time domain. It shows the raw composite signal, the voltage just fluctuating up and down over time, typically over like a 5-second window, the source says.
Ah, so that's the trace that looks like the classic brainwave recording.
Exactly, and it's literally the sum of everything you've added, all the individual brainwaves plus any artifacts you dialed in. It's the final mixed signal.
Okay. Now, here's something the source really flags as important. You mentioned those dotted ideal overlays on the power spectrum graph. And then there's the actual computed spectrum, the filled-in blue area from the final mixed signal. The source says they don't line up perfectly, right? Even if you only have one main wave active.
Right, and that's not a glitch. It's actually a really key concept the simulator helps illustrate visually. It's fundamental to how waves work.
Okay, so why don't they match? Why isn't the final spectrum just a perfect stack of those ideal shapes?
It comes down to interference. The source uses a great analogy. Think of that final blue spectrum, the one computed from the waveform, as a cocktail.
A cocktail.
It's made by mixing all your ingredients, delta, theta, alpha, beta, plus any EMG or EOG noise you added. Those dotted overlays, though, they're like looking at one pure ingredient in isolation before it got mixed into the drink.
Okay, I like that. The cocktail analogy works. Things blend. They don't just sit there separately.
Precisely. When you add waves together in the time domain to create that single up and down waveform trace, they interfere with each other constantly. At some points in time, the peaks of different waves might line up. They add together, making a bigger peak. That's constructive interference.
Okay, adding up.
But at other moments, a peak from one wave might align with a trough, a dip from another wave. They partially cancel each other out. That's destructive interference.
Ah, okay, so this adding and subtracting is happening all the time along the waveform.
All the time across the entire signal. So when you then take that final combined interfered with waveform and run the FFT on it to see its frequency components.
The result isn't just those neat ideal curves stacked up.
Exactly. The resulting power spectrum, that blue area, is more complex. It's, lumpy, as the source describes it. It reflects how those pure components actually interacted over time to create the final signal you see.
So the overlays show the ideal ingredients, but the blue area shows the actual cocktail after mixing and interaction.
Perfectly put. The overlays are still super useful. They guide your eye, showing you where the energy should be concentrated based on your settings. But the blue area is the reality of the combined signal's frequency content. The simulator makes this relationship much, much more intuitive.
Yeah, you can see it directly instead of just imagining equations. It shows why the sum of the parts looks different in the frequency domain compared to the time domain.
It really demystifies that link between the raw signal and its frequency breakdown.
Okay, so let's wrap this part up. What does this all mean? We've taken this deep dive into the EEG signal simulator. We understand its purpose education, algorithm testing.
Right, we looked at its parts. The brain state presets for typical patterns, the artifact simulation is super important for understanding real-world challenges like muscle noise, EMG, and eye blinks, EOG.
And the fine-tuning controls.
Mm-hmm.
Simple sliders, but also that customized mode for setting specific frequency, bandwidth, amplitude for each wave, delta, theta, alpha, beta.
Then the visualizations, the power spectrum, using the FFT to show power per frequency. That's the frequency domain view.
And the simulated EEG waveform, the raw signal over time, the time domain view.
And we really hit that key concept why the actual signal spectrum, that blue area, looks different from the ideal overlays.
Right, it's all about signal interference. Constructive and destructive interaction between the waves and the time domain.
Meaning the final frequency breakdown isn't just a simple sum of ideal shapes, it's more complex, like that cocktail analogy. Seeing that visually is a huge takeaway.
Absolutely. And the source also touched on future ideas for a tool like this.
Yeah, some exciting directions. Adding more waveforms like gamma waves, those faster frequencies above 30 hertz, often linked to higher cognitive stuff.
Okay.
Simulating more artifact types, maybe EKG from the heart, or that annoying 50 or 60 hertz hum from power lines.
Oh yeah, that hum gets everywhere.
Definitely. Also, more advanced analysis like spectrograms, which show how the frequency spectrum changes over time. Multi-channel simulation to look at patterns across different scalp locations.
So simulating a whole head of electrodes.
Potentially, yeah. And even maybe importing real-time data. Lots of possibilities.
So ultimately, this simulator, as the source presents it, it's this dynamic learning tool for newcomers, right? But also a practical utility for people already in the field.
Exactly. It makes the complexities of EEG, which can seem pretty daunting, much more intuitive and interactive. It helps bridge that gap between the raw squiggly lines you record and the frequency information hidden inside them.
By letting you build it up yourself and see the connections.
Precisely. It demystifies that relationship.
Which actually leads to a pretty important question to leave you, the listener, with.
Okay.
Given how dramatically these artifacts and just the natural interaction between different brain waves can change the signal we actually see, change it from those clean, ideal components.
Yeah, in ways we can't always project perfectly in real life.
Right. So how might that reality influence how we interpret real clinical EEG recordings, where we don't have the luxury of knowing the exact ingredients that went in?
Good question.
And what does that imply for building tools like brain-computer interfaces that need to be really robust and accurate? How do they deal with all that inherent noise and complex interaction to reliably figure out what the brain is actually doing?